Hey guys, thanks for coming to the speech paper reading session again. And this week, China launched its third aircraft carrier named Fujian. Well, one interesting thing is that it uses a special technology which is also employed in the speech processing. What is this? Let's take a look at the video first. You can see the two black boxes. Underneath these two boxes are the electromagnetic catapults, which is used to project aircrafts. Well, one thing you may notice is, let's continue to look. Well, it's beautiful. Okay, here you go. So you can see the tower, right? And it's like the air traffic control tower in any airport. But what is this? If you can see my mouse, and the flat panel, which is not perpendicular to the surface, but with a certain degree, it's facing upward, but it's not facing on top. And this is what? This is radar. And this is mostly, it's called a phase array radar. And mostly on aircraft carriers, it is called active phase array radar. And you may ask, wait, what is this type of radar? What does it do? So basically speaking, a radar can be, especially phase array radar, can be categorized into two main categories. One, passive phase array radar, or active phase array radar. When we talk about the passive radar, it does not send signal, so it will just passively wait for any signal coming from the aircraft itself to hit the radar, and the radar would analysis where the object is. Three things: where is the object, how far is it to the radar, and what is its velocity vector. Three things. Okay. So what is different of active phase array radar is that it does not passively sitting there for the signal to come in. Instead, it will send signals in certain directions with either fixed frequencies or changing frequencies. So lots of time you see in the Hollywood movies, okay, you saw this type of some radar screen with some beam that going around and around. That means it's an active phase array radar. It will try to scan all the objects near it by sending out signals. So when the signal hits the object, and the object would reflect the radar signal back to the radar. So the radar knows, okay, this is the signal I sent, and now I received the signal. So basically, by measuring the delay, they know where, how far the object is to its radar, by measuring the signal intensity, they know where what's the direction of the object. And of course, by further analysis signal, because it's keeping going around and around in a very fast speed. So by taking a look at where the objects in 2 time intervals, they're able to know what is the velocity of that flying object. Of course, the active phase radar array radar is more accurate compared to the passive array radar, but the cons is that it might be discovered by the aircrafts, and it can bring some attackers, missiles. But the good thing of the passive phase array radar is that it doesn't send signal. So it's relatively safe, although it's not that accurate compared to the active array. And what is interesting here is the passive phase array radar is exactly the same technology which is being used in the microphone array, which is being used in the speech processing and for the speech recognition, even in the Alexa, the small speaker of Alexa in your home. So let's take a look. And today, I think I will start from a very classical paper. Its name is Microphone Array Processing for Distant Speech Recognition by Dr. Komatani and his colleagues. So first of all, let's take a look at the description of the scenario, okay? So these people first describe a very simple scenario, which all the microphones are sitting on one line. So this is called a line-shaped microphone array. And you can see these M0s to MS-1 means there are RS microphones, okay? And there is a target source, sound source X. So here is different than the aircraft carrier and the flying aircrafts game. The flying aircraft doesn't want it to be detected by the radar. So anyhow, it tries to not to send any signals out from it or reflect any signal from it. So this is why people have the F-117, the Phantom aircraft carrier, aircraft. But in the speech recognition, usually the target source means the target speaker, the guy who is talking to the microphone array. So he or she wants to be listened. So it's definitely a signal which can be captured. So suppose the speaker is fairly close to the microphone. Okay, this is the case. Okay, you can see it's very close, and each microphone might get the speaker sound at the same time. But this is not the usual case. Imagine that suppose you have an Alexa at home. You never get your face close to the microphone array and speak, right? Usually you're about at least 3 feet or 5 feet or even 10 feet from it. So this comes to the case shown in the figure B, which means the plane wave, okay? Means when the waveform are hitting the microphone array from a distant location. So you can see the waveform beam can be regarded as a parallel to each other. So this is like this. And it's fairly easy to understand if you learn some geometries, okay? Suppose these two microphones has the distance of D, and you want to estimate the direction of the speech, or where the speaker is coming from, aka estimating the theta, okay? And then certainly you can do this by seeing, suppose you have a spike arriving at ms at this time, but as for this waveform, this spike, although it comes to this point at the same time as this waveform, but it will still need to travel d times cosine theta to hit this one. And we know we can measure this for sure. Suppose that we measure the delay and we know this is tau. And tau times the speed of the sound transmitted in the air, this distance is equivalent to d times cosine theta. And this is, you can definitely tell this theta by doing this, right? Is r cosine theta cs times tau over d. But it's pretty much a game of measuring the tau, okay? Really understand. And in the passive phase radar, in the passive phase array radar on the aircraft carrier, or some not on the aircraft carrier, it uses the same technology to find out where the direction of the flying object is. You may ask, how do I know how far is it from me? Okay. So in speech processing, people usually don't care about how far is it from you. Okay. Because anyhow, you're gonna recognize the speech, and if it's too far, the volume might be low, but you can still hearable. But in the practical phase array radar on the aircraft carrier, so it needs to know how far is it from you. So basically, it's very simple, right? Because it uses the active phase array. So the signal coming to the array is indeed a reflection of the signal is sent out, okay? So you can see, suppose you send out a time t1 and hit the flying object at a certain time t, and it comes back at the time t2, okay? So the duration is delta t equals to t2 minus t1, right? So it's fairly easy to know that the distance, the distance L equals to CS times delta T over 2. Very easy, right? Well, the third thing is the velocity of the aircraft. It's very simple because the active phase array is sending out the signal time by time. So you just measure, suppose you have a Cartesian system, then at the time t, you got this one with the theta 1 and L1 here. At another time point, okay, you found, okay, this guy is located at this direction, but with this location. So definitely by doing the geometry, you know, you can calculate what the S is. And because you know the duration for between the two scans, so the velocity definitely equals to the S over the delta T. This is the duration of scanning, okay? And of course, the V is, you can get a vector, right? For sure. I calculate the scalar value here. Okay, well, let's come back to the speech. So in speech, you may ask why people are doing this beamforming. They're not trying to hit a flying object, right? The biggest objective of using the phase array in the speech processing is to do the beamforming. Okay, beamforming, or say I want to get a better estimate of what is the source signal X. Why? Because when the X signal is traveled through the air until it hits the microphone array, you can definitely see that this X might hit the wall and come to the microphone array. This is called echo. It may also some pervasive environmental noise coming into the microphone. Okay, this is called the noise, right? And the noise, it could be additive noise or convolutional noise. So all these type of noises coming together. So indeed, when your microphone array corrects the voice, it's not the original X. It's a distorted X. So this is why they are trying to use microphones laid in a special shapes. So in this case, it's L-shaped. Sorry, it's a line-shaped. But it's more commonly people are using L-shaped microphone, something. So this is an L-shaped, okay? Sometimes they use L-shaped. And sometimes they use array-shaped. Or sometimes they even use spherical arrays. So say I have a microphone array on the different locations of a sphere, okay? Different sort of arrays. What people do this because they're trying to use different ways to better estimate the original signal X from the captured signal X prime. And X prime is a vector. So it goes from the signal captured at the first microphone to the last microphone. Okay, it's a vector. I use this notation, but the author used this notation. You can see they use the F. You can see, suppose the original, here they use a very simple assumption that they're saying that, okay, there's no noise at the beginning, and the N signals you collected from the N microphones are just a delayed version of the original signal, okay? This one. And they're saying that, okay, mathematically, they're saying, okay, you can do this. You take the FFT of the vector f of t, then you get the vector f of omega. So f of omega can be written in this style. So f omega is the transform of ft, but v of k omega is an array manifold vector. This is very straightforward. As long as you have a delay, you will have the form of complex signal like this. So this is a one-to-one mapping. See? And then now the next step is that suppose I want to work in the frequency domain. Okay. What does that mean? So suppose that all the microphone array, they calculate these vectors, and I converted these into the frequency domain. Okay, then what I want to do is for each microphone, I want to do a multiplication using certain weights on each microphone, and multiply that with the signal at that microphone, and then eventually want to add them all together. And then hopefully I can get the original signal, which is y of omega, the frequency of the original signal, okay? So the simplest beamforming algorithm, which is called delayed and sum. Indeed, most of the phase array radar, they use this algorithm because it's simple, robust, and it works. They're assuming that these things equivalent to this, and suppose you do the replacement, you can get the y equals to this, and this definitely you're supposed to get the original signal f of w, right? Then by all the deduction, you'll get this very satisfying equation. So that means what? So suppose you want to solve the vector of w at the different frequencies. So the solution has to satisfy this equation. And as we discussed it before, the V of k omega can be calculated using this one, right? But here comes the question: Can you discover the issue? Okay. The issue is that the tau 0, tau 1, and the tau S1 has to be estimated, right? Because you don't know the delay. This is the factor you want to estimate. So then you can see that there has many solutions to the W. So you need some extra constraint so you can get W. And people later, people come up with a criteria. What criteria? Or they come up. This is just a condition. Usually something like this, subjected to this condition. But the thing is, what is the equation or the real equation you want to maximize or minimize, right? This is an optimization issue. You want to find the W that can minimize something. So the smart researchers, they propose something of this. It's called they're saying that, okay, because it's in real world scenario, it's not that simple to just the Y signal you collected is just equals to the original signal X. No, that's not true. Usually the collected signal is a summation of the original signal plus the noise signal. That's your case. It's simplest. Indeed, it is the simplest case. They're saying that, okay, suppose you applied, you try to apply the weight onto the x of omega. You also applied the weight factor onto the noise. So I want to minimize the noise energy after I did the filtering or the beamforming. So what is the afterward noise energy? It's calculated in this way. And they want the noise after the beamforming to be minimized here. And so this is optimal. This is optimization criteria. And don't forget this, subjected to this one. And then after they solve the equation 6 and 7 together, they come up with the solution here. it's standard convex optimization issue. And you can definitely see that this one times VK of W equals to 1, right? This is all just a get over this, get over this, and get over this, right? It's equal to 1. But there has a lots of issues. First of all, this solution is not very stable because getting the inverse of a matrix is sometimes can be ill conditioned. Okay, the matrix can be ill conditioned, and the solution is not stable. So this is why people are trying years after years try to improve this MVDR beamformer. But so far I see lots of beamformers, they are still doesn't change very much from the MVDR beamformer. Okay, and you can see this is our variations. Okay, we're trying to do something. Okay, so you may ask, okay, now I have come up with a special beamformer which minimizes the noise. So what can I do later on? So that's a good thing, right? So you can estimate a relatively cleaner signal, which is very close to the original signal. That means you have better understanding of the scene, and you could use the beamformed signal to do the speech recognition. And you can see these guys are coming up with this. And then let me quickly show you the results, how good they can do, okay? So you can see the table here. If you're just using the vanilla 1 array channel, okay, this means the microphone array, the number of microphone is just 1. You get a very high WER, but you can do pass after passes, right? Then you can eventually come up with something like 28% WER, very high. But if you're using the very vanilla beamforming, which is delayed and sum, very vanilla algorithm, you can reduce the error by half. And suppose you're using the MBDR beamformer, the vanilla minimum variance distortion response beamformer, you can further reduce the WER by I think it's not very much aligned, but yeah, you can get another, I guess, at least 10%. This is like almost a 50% drop. And then people come with another fancy beamformers, and you can see those are the beamformers, and they can I think they also propose something like a SD ambient beamformer, especially I think maximum negative entropy, entropy. There's something they propose. It works fairly well. You get another, definitely from here to here, you get another 10%. And this one, to be frankly speaking, I don't know what this one seems. It works even better, at least 15%. And you may say, what if you know almost the exact original signal? Let's think like this. It's called close talking microphone. So you already no noise is getting in because you're so close to the microphone. The signal to noise ratio is infinity. So you already will assume that there is no noise getting in, and you can get 6.7. But definitely you can see that there is still another 50% to go from their best beamforming algorithm to the close-talking microphone, which means 10 years ago it has a long way to go, but nowadays it still has a long way to go. Although people have to develop the new algorithm, for example, is called some data augmentation. You can use noise to augment your data, try to simulate some training data under noisy condition. But my experience is that you can probably get about some accuracy around 8% at least. Not just 8%, probably just around 9% at most. So you still has way to go to get as good performance as the cross-talking microphone. And this is their setting. They're using, I think this is a Kinect camera a long time ago. All right, I'm gonna stop here. Thanks for watching and see you next time. Bye.